In this video, we will discuss capacitors and aim to provide an intuition into the physical process of operation. This high-level description will be converted into a mathematical model, which will aim to discuss the usage of complex numbers in an AC analysis of a capacitor. The differential relation between voltage and current will be derived, and this will be used to derive the equivalent impedance of a capacitor. For those unfamiliar with complex numbers, don't worry. There will be an overview of everything you need to know. Firstly, we can consider the animation shown. The idea is that a voltage is applied across a capacitor, which causes a current to flow. Electrons will move from one plate of the capacitor to the other, and there will be a net positive charge formed on one side. It should be noted that electrons flow opposed to the conventional current. Additionally, the positive charge forms from an absence of electrons. This causes an electric field, which goes from positive to negative charges. The dielectric is not essential to basic operation, but it is important in future considerations, but this will not be discussed here. The end result is that there is now energy stored within an electric field. If you were to replace the battery with an arbitrary load, a resistor for example, the capacitor would discharge and act as an energy storage device. Although we aim to consider the AC analysis of a capacitor, this process still represents a good way of thinking about a capacitor, but the current shown so far represents a DC model. The purpose of including this was to understand the meaning of capacitance, which is the change in the charge for a given change in the voltage, or C equals dQ by dV. From the definition of current, dQ equals I dt. The differential relationship can be obtained as follows. This is very important for all analysis of a capacitor, including the derivation of impedance, as we will see, as well as analyzing the charge and discharge transient of a capacitor. Now we need to take a short side note to review the use of complex numbers. If we start with Euler's identity, then e to the j theta equal cos theta plus j sine theta. J is equal to the square root of -1. Using the identity, we can express this as a complex exponential. If you substitute pi over 2 into the identity, you will see that this equals j. So, what is the meaning of j? It doesn't physically mean anything, but it does provide a means of making sense of mathematical expressions, and in electrical engineering, it gives a representation of the phase. If we consider the diagram, called an Argand diagram, we can see that if the y-axis is imaginary, it is on a scale from 0j, 1j, 2j, and so on. The x-axis is the real axis. So, a complex number can be represented by a magnitude and an angle. Thus, trigonometry can be used. So, if we have a number on the real axis such as 2, then multiplying this by j immediately changes the point to 2j, which is on the imaginary axis. Thus, by a very simple multiplication, we can represent a rotation where theta has gone from 0 to pi over 2. In other words, multiplication by j is a phase shift of pi over 2. Now we can see that a representation of cosine omega t is just the real part of the complex exponential shown. Practically, this is the only part that has any physical meaning. Thus, we perform operations on the complex exponential and then take the real part of the result. Don't fall into a common trap. It is true that cosine and sine are phase shifted by pi over 2, but j times sine does not equal cosine. The way to think about this is that the input may be cosine, but that is only the real part of the input, and that the operation with j must refer to the full complex representation. If we return back to the differential relationship and then substitute a complex exponential form for the current, then we can obtain V. All previous DC analysis focuses on an equation of the form V equals IR. But if we replace R with a complex impedance, Z, then, for a capacitor, we can easily cancel the exponential and rearrange to obtain Z. Included are two commonly seen forms, which are equivalent by considering multiplication by j over j, which equals 1. Remembering that j squared is equal to -1. Now, because we have used a form similar to Ohm's law, then we can obtain the series and parallel relationships. Finally, we can see the practical use of this when considering the real parts of the complex exponentials. For simplicity, we can use a sine and cosine wave, which have a phase shift of pi/2. For a capacitor, the current leads the voltage as it is effectively seen before the voltage waveform, as the peak of the current waveform would be experienced first from t=0. Please make sure to support this channel by liking and subscribing.